The last example in 6a, we need to look at logarithms and differentiating logarithms. Now I'm going to do this slightly differently to your textbook because I want to get the general formula for logs, then we can use that. So the key thing here to know is that if we have the derivative of log of x, that's equal to 1 over x. All right. Now the important thing here is that x cannot be 0 and it can also not be a negative. So what we use is we use modulus signs around the x, or we can just say x is greater than or equal to 0. And so here, if you wanted to do that, you could just do x is greater than or equal to 0. Oh, greater than 0, I should say, not equal to. You can't have 0 underneath. Okay, so that's the key result, I guess, for logs. Now I want to derive the more general result for the logs, which is if you have to differentiate d dx, the logarithm of a function, okay, of x. I'm going to use u of x here. All right. Now what we're going to find is that if we differentiate this, we're going to differentiate what's inside the bracket, so the derivative of ux times the derivative of the whole thing. And this is because we're really using chain rule. So what we're going to do is we've got a ux there, so let what's inside the function be u, which we already have. So we're going to let y equal log of u. Okay, so we know that the derivative of u, we know that if this is u, well, we have du dx, and dy du, we've just got something in here just like an x. Derivative of log u, well, that's going to be 1 over u. So by the chain rule, we actually have dy dx, so the derivative of this thing, if we let all of this equal y, which is du dx. Now it doesn't matter what this function u is, we just need its derivative, times dy du. And the cool thing is we know what that is, it's 1 over u. So we actually find that for any log function, the way to express a log of any other function is the derivative of what's in the bracket. So this is what's in the bracket here, u. The derivative out the front times 1 over u. So whatever's inside the bracket goes underneath as a fraction. The thing you'll notice here is that there's no logs left over. When you differentiate a log, you actually don't end up with a log in your answer, you end up with a fraction. So that's a really important thing as well for when we differentiate. So this is the key result here, and I'll actually write it in a slightly more formal way here. So the derivative of log of a function of x is u dash. I'm just going to write this as u dash x, and it's all going to be multiplied. So this is actually a numerator by 1 on the top, and the denominator is ux. So whatever is in the bracket of the log goes underneath as a fraction, the derivative goes on the top. And that's a huge result. It's so useful. So definitely a big square or highlight that in your book somewhere so that you know that one. It's nice, that one and the exponential from the previous worked example. So now what we can do is actually go into solving these problems. So the first one we've got is find the derivative of log, and it's natural log because it's got the little e, log of x, and it's log mod of x. And we know that when we differentiate a log, provided that x is non-zero, and here it doesn't matter actually that it's negative because we've got the mod around it, that's just 1 over x. That's all we have to do. Okay, so it's not very extreme. We can also be, if you want, more particular about it. So what we could do is actually say, okay, when x is greater than 0, that's what our result would be. What about if we had d dx log of mod x when x is less than 0? What would happen? So we know that in doing that, we'd have a negative x. I'm just going to put a negative there. Okay, and we'd have our derivative, and we're going to use this result here. The derivative of what's in the function goes on the top. Derivative of the function is negative 1. The function itself goes underneath, negative x. And check it out. The negatives disappear. So that's why when you're dealing with these types of functions, the fact that you have the modulus in there is really kind of, I guess, overkill, in the sense that this result here actually gives you 1 over x anyway. So for this question, the derivative of log of x. Whether it's positive or negative, the answer is 1 over x. Okay. For the next one, for b, we've got the derivative d dx of natural log of sec x. Okay, what we have to do is remember what sec x actually is. What is sec? Well, sec is 1 over cos, and we've got the modulus signs around this because the log has to be a positive number. And we've also got this result, or this particular restriction on x here. Now this is basically stopping cos x from being 0. We know that the denominator has to be non-zero. If x was, like, for example, pi on 2 or 3 pi on 2, etc., this would be 0. Cos x would be 0. So this 2k plus 1, anytime you do a multiple 2k plus 1, where k is any integer, this is even, because obviously something multiplied by 2 is even. You add 1 on, that's an odd number. So this is any odd number pi on 2. So 3 pi on 2, pi on 2, 5 pi on 2, that's what this actually is here. So this is saying all of those multiples of pi on 2 that don't give you pi or 2k pi, those are not included. So we don't end up with a 0 denominator. So to finish off, we're now going to differentiate this guy here. So I'll just move this onto the next page. So we're nearly done. Move that up there. So now to deal with this one, what we can do is actually use the result that we looked at before. And I'll bring this over as well. I just love this. It's just it's just so beautiful, the fact that you can differentiate a log and your answer doesn't have logs in there anymore. So we then have, so the function that's inside here, we have u equals 1 on cos x. That's what the function is inside the log. What's the derivative of that function? We want du dx, because that's the u dash on the top. We need to know what that is. So we can actually use quotient rule here. So for quotient rule, what we're going to do is we're going to just use different variables here. So instead of u, because we don't want to confuse the u that we have here. So let's call v and w. Let v equal, or actually might w. W is the top line, v is the bottom line. And we're going to use the quotient rule. All I've done is I've just replaced the w and the u with the w so that we don't get confused. So it will be w dash v plus v, oops, take away v dash w on v squared. Derivative of w, derivative of a constant is 0, awesome. Derivative of cos is negative sine. So the quotient rule here will actually be these two multiplied together, which is 0, take away these two multiplied together, which is just sine x, over the top of v squared, which is cos squared x, becomes a positive. So what that means is that our derivative of 1 over cos x is actually going to be sine x over cos squared x. So that's our derivative, our u dash. Oops. U dash x. So to finish off our question here, we're trying to differentiate a log, and we had a function inside that log. Okay, so the derivative of the log of 1 on cos x equals the function itself underneath the fraction. So it's going to be what's actually in the bracket, 1 over cos x, that's the function. All of that function inside the bracket is the u. And then the derivative, u dash, well, we found it was this, sine x over cos squared x. So that's actually the u dash. Now that looks really ugly, so I'm going to actually do that trick of bringing what's on the bottom all the way up to the top, and the one to the middle there. So we have sine x cos x over cos squared x, and you can see that you can then cancel. Boom, boom. So we have, our answer is sine x over cosine x, which you'll recognise then as tan x. So that means the derivative of our original function which was log of 1 over cos, which is actually sec x, is simply tan x. How beautiful is that? It's quite amazing. There's this link between sec and tan everywhere. We know that from one of the earlier examples we did where we had the sec squared equals 1 plus tan squared identity. So in this particular case, differentiating a log, remember that it's the function itself as the denominator and the derivative of the function as the numerator. And we found the derivative of log sec x is simply tan x. So the key result here is really knowing how to differentiate a log. The simple thing for differentiating logs, derivative of log x is 1 over x, provided that x is bigger than 0. And the more general form, derivative of log of a function of x, u, is u dash over u.